It was the year 2100. Humanity had made unprecedented progress and achieved first contact with an advanced extraterrestrial race. In an act of goodwill, the alien race provided humanity with their unique knowledge of dark matter technology, propelling us into a new era of scientific discovery and exploration. Fortunately, we were able to seamlessly integrate this revolutionary technology with our existing systems with minimal issues thanks to the ingenuity of a few researchers from ASPLOS 2023, decades prior. Let's now take a journey back in time to witness the achievements of these pioneers. Hi everyone, my name is Aditya K. Kamath.
And I'm Sujay.
And today we'll be presenting herding llamas using LLMs as an OS module. In a world where memory technology is constantly evolving, the operating system is forced to adapt to this ever-changing domain. As newer technologies emerge, the search for efficient data placement strategies and memory tiering consumes countless hours of research and demands immense innovation, as we can see here. This is only half the problem. Implementing these designs as production-ready modules also consumes precious developer time. While we grapple with this problem, it is also important to prepare ourselves for issues we will face in the future. With the untimely demise of Moore's law, we find ourselves in a golden age of explosive architectural growth. However, every new processor places a greater burden on programmers by requiring them to learn and code in unique languages. Nonetheless, the research community is engaged in efforts to unify hardware architecture and compiler infrastructure. Initiatives such as RISC-V and MLIR offer promising avenues to simplify the development process and enable more efficient collaboration. We envision a future where programmers can code in any language that they prefer and execute this code on any hardware architecture. However, this vision poses a new challenge. Who decides the hardware that the code should run on? To reduce the burden of the programmer, we believe that the OS is best equipped to tackle this challenge. As with memory management, this would require significant concentrated research effort to solve, and with every new type of processor, the wheel would need to be reinvented. Wouldn't it be nice if we didn't have to reconfigure systems every time something new pops up? Ideally, we would want an operating system that would just work, and would need only minimal adjustments to support new technologies, while still being able to take advantage of their performance-enhancing features. Unfortunately, achieving this is not a trivial task. Each new hardware device has its own quirky properties that make universal solutions impractical.
And to solve that problem, we propose LLaMaS, which is a machine learning-based operating system module that aims to adapt to evolving hardware technologies. Now, integrating a new device into the system is as simple as describing the system properties in text. So what exactly is LLaMaS? Well, LLaMaS is a hybrid machine learning model that has a front-end LLM. Users can describe the system with a front-end LLM, and users have to do this only once when the system configuration is being changed. We can also provide the program binary and source code to the front-end LLM. The LLM would extract useful information and pass it on to the back-end model, which would make decisions in runtime. Let's take a closer look at how this works. A system engineer would describe the system components and the properties of the various components. Say you have a new memory technology, all you have to do is describe the properties in text, and the LLM would extract features or embeddings from this. The backend would then use these features along with real-time stats such as hardware performance counters to make operating system decisions. Now, we could have different backend models for different tasks, like one for memory management, one for scheduling. Now, to test the feasibility of this solution, we ran some experiments with ChatGPT, which uses GPT 3.5, a well-known LLM. So we tested out with a new memory technology. We created a new technology called repetitive access technology, or RAT. And the idea was that RAT would provide low latency for data that is accessed frequently. The model was able to extract the features of RAT and decide that variables that are accessed repeatedly needs to be placed in RAT. It generated a list which we verified and were surprised to see it was correct. We also saw that LLaMaS could make scheduling decisions given to functions and to hardware platforms, CPU and GPU. The model was able to identify what to run on what platform. It identified that the matrix multiplication is highly parallelizable, so decided to run it on GPU and pointer chasing on CPU. Now, these results have been promising, and we believe that cool and wild ideas such as LLaMaS would see the light of day in the near future. To wrap it all up, designing the OS every time a new technology comes out is challenging. We might have wild and crazy technologies in the future, and we need a solution that would integrate all of these devices seamlessly. And LLaMaS does just that. It's flexible and reduces the effort required to incorporate these devices into our existing systems. Thanks for listening. If you have any questions, please feel free to reach out to Aditya or me.